thing we've done so far.
Oh, this is okay.
It's just a summary. We talked about all these concepts last class and just put them all in one
Right.
slide.
Yeah, I was gonna say,
We'll go
this
through it.
looks the same, but it,
And it's,
I know we talked about it, but
we
it's.
talked about basis states, talked about the wave function. We talked about how these numbers that are on the outside of the basis state say something about the probability of observing that state. And that total probability has to be one. We talked, I can bring it over actually. Just to convince you of that.
I'm convinced.
I convinced you guys that for the deflection states, the total wave function is the sum of the basis states of up and down deflecting.
Okay.
The numbers on the coefficients have something to do with the probability. We showed that the probability of observing a given result is its coefficient squared. And the sum of all the coefficients squared has to be 1 because the probability of anything happening. That's what we call normalization. So I'm just summarizing an hour's worth of work into one slide. We'll go through it again and we'll go look at examples. Again, this is such a good class for example. I have tons of examples for you. It's kind of a, it's ironic when we talked about, we have time. Okay, so I'm just going to chat for a minute. It's not really a class. In thermodynamics, last semester, it was hard to give you guys examples in some sense because to construct the thermodynamic functions, you tackle things very generically. And then you apply them and, we can go do a chemical reaction, calculate the enthalpy and stuff like that. It's hard to demonstrate the concepts outside of that, like outside of these like specific cases. Here, the thing is quantum mechanics was developed from experimental observations. So every insight that we can come up with, I can show you an experiment that demonstrates it because every single one of them was derived from an experiment. That's the nice thing about this. Some of the experiments are very strange, but they are all experimentally realizable statements. Well, look at this slide. We're going to talk about this slide quite a bit. For a really central concept. Come back. I would like to use the restroom. Starting. I think that's the time for that.
Oh, no, I think she said when we just totally, I don't want to do that. I'm so sure.
That's what she said.
The calculations are already done. I'm sorry. Then she was. Yeah. It's a 4x4. That makes sense. I think like also interesting. I see we're all like this, but for every person. Yeah, we'll start getting. Like a thousand killers are getting like, although time first, like, it's so bad. Yeah, my work. But it's the first year I was partial. To only write like sections, but then after that, all. I don't really. I don't know. I don't know. Hey guys, we're here.
Let me make sure everybody. Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. We have one short person. All right, I'll just get started. Homework's out. I don't know if anyone's looked at it yet. I assume you'll start looking at it tomorrow when Kayla and Allison's sessions start up. But it's okay. Everything we're going to talk about today is the homework. So the homework is, I'm going to give you examples, of course, but the homework is in some sense the example of all of these. It demonstrates all the concepts about the wave function and this topic we're going to talk about, which is we're talking about the state of the atom that we're measuring in our deflection experiment, for instance, right? Whether it's up deflecting or down deflecting, and the wave function encodes that information. We haven't talked about the instrument itself, the measurement device. So there's two parts of an instrument of a measurement. There's the device and its operation on the atom, which might just be a measurement. It doesn't have to do anything special. You can just measure it. And then there's the atom, which has a wave function. All right, so we need to think about how a wave function, which we talked about last time, it's just for the deflection, it's just a vector. I'll go back to my slide from last class to remind you of this construction we did, because I know it's been about a week. And this construction is the homework. So you're going to see this in the homework. And the idea is that we choose vectors to define our base results. Our base results are up deflecting or down deflecting in the z direction. That was our initial experiment. I'm going to just make sure I'm not muted. I'm not. Okay, very good. And so the choice that we make is to define each of these results by what's called a basis state, a basis function, which is just a vector that defines the pure result, one of the two pure results. There's only two results of the experiment, so there's two base states. The base states are z plus and z minus. And the way I construct them is very simple, is I write one to be a vector 1, 0, which is just in the x direction effectively, and one that's in the y direction, 0, 1. Okay, so these states represent the two, what we call the pure states of our atom. They're the two simplest state explanation or descriptions of the state of the atom, going two options. And the claim that I have is that any state of the atom can be a sum of these two. All right, so I can take a little bit of up deflecting and down deflecting and mix them together to create some arbitrary vector in some direction. And the coefficients of these vectors, they just tell us the probability of observing one of the given results. Okay, so it just tells you in some sense the state of the atom as it goes through the measurement and what the potential outcomes are. Right? It just describes the outcomes. Right? The cool thing about quantum mechanics is that if we can describe the outcomes and understand the math and the statistics of outcomes, that teaches us something about the properties that generate those outcomes. Right? So we kind of have to, we're like looking at the output and we're trying to peer in to understand what's going on underneath the hood. We can only do that through deduction. But there's only two possible results, up and down. So any possible result that we can see out of our experiment is some sum of the two. Okay, could be 50%, 50%, it could be 90, 10, it could be 199. It doesn't matter. Any combination is acceptable. And what that leads to is that if you think about these vectors as possible states of our atoms, then there is an infinity of possible states in the sense that I can draw a vector in any direction around this circle, which are always some combination of the up state and the right state, right? If you think about the plus state as being the x component of the vector and the minus state being the y component, then I can have any x, y component as long as that vector is pointing at somewhere around that circle, right? Any combinations. The important thing is that we have to maintain what's called unitarity or causality, which is that the total probability of anything happening is 1. Probability of 1 is the same as saying 100% chance. Exactly the same concept. We just divide by 100. So we know that the total probability of observing anything has to be 1. So the idea is that these vectors, if they represent the potential outcomes of our experiment, the total length of that vector can't be more than 1. Right? So that probably makes sense, because if we had an atom that is just z plus, meaning that it deflects up 100% of the time, that vector is just 1, 0. It has length 1 by definition. It's a unit vector. And z minus is also a unit vector in the opposite, the perpendicular, the orthogonal direction. Right? So you've got these two length 1 vectors that you can construct any possible state of your atom from, and they all have to be length 1. So all the possible states span, in some sense, this circle in this deflection space. All the possible states are in a circle of radius to 1. Okay? Don't think about this circle as something representing something physical that you can touch. It's what's called a phase space, parameter space. It's just kind of what I like to think of it is that you can think of each point on that circle as being a Dewey Decimal code for a given state. And your vector points to whatever Dewey Decimal entry for your atom is represented, the atom represents. It tells you where to go look for the state of the outcome of that atom. And it's a natural kind of mapping of the atom to this indexing, if you will, of the results. Okay? So it's not really a physical space that it's traveling through, but rather it's you can think of the wave function as something that a pointer that points to a specific state that can be encoded directly by this construction. Okay? We can do more work to make a more physical picture of this wave function. And we're going to talk about that hopefully today or Wednesday. Something that maybe makes more sense, like you can touch and feel it, like something that exists in space. You're going to have to think about how you represent this in space. Okay. So that's all I need to say about this. We can now go back to the original, the review slide I have. And so any quantum mechanical system, right? When I mean a system, I mean atoms, electrons, it can be anything. Right? Any object that we want to assume is quantum mechanical, we want to represent it quantum mechanically. We choose a wave function for it, construct a wave function for it, which is just, as we saw, a vector. We'll see that there are other ways than vectors to do things. Vectors aren't always convenient. And I'll show you a great example, hopefully today, of where vectors might not be very useful for us. And so a wave function is constructed from a set of basis states phi. Of course, in the deflection case, there's 2 basis states, up and down, right? And which correspond to each of the possible measurement results of the experiment you're doing. Okay? So we construct a wave function contextually based on the experiment that we're doing. If we're measuring something, thinking about where atoms lie in space or where an electron exists in an atom, it's probably not useful necessarily to think about these arbitrary vectors. We want to think about where the electron lies in XYZ coordinates, right? So then our wave function is going to be a function of X, Y, and Z. That's not a vector, that's a function, right? It's something that you can plug in and plot, integrate, take a derivative, all of these things. We want something like that, right? We want to know exactly in space where the electron is. So it's not really clear how we go from this perspective. That was very convenient for our deflecting atoms into a space where we can talk about X's and Y's and Z's. Okay? But we'll find out that this math works exactly the same way, but with functions instead of vectors. And the idea is that you have this wave function, a vector. It's constructed from these basis states, of which there may be infinite. Of course, in the case of a deflecting atom, silver atom, there's only 2 results, so you get 2 base states. But there are obviously experiments where there might be an infinite number of possibilities. And wave functions satisfy effectively, they satisfy more properties than this, but these are the 2 that are relevant for us right now. One is superposition, which is saying that if I have a set of basis states, I can combine them linearly and just add them together any way I want. And the output of that is also a wave function of the state. Okay? So I can construct, in some sense, what it means is that for my deflecting atom, I can put the atom in any state that gives me any probability of deflections. Okay? I can put it anywhere on that circle. That's all this is saying. And it's also normalized, which means that the total probability of anything occurring is 1. And the probability of an individual result occurring is the coefficient on the outside square. So let's look at a quick example of that. Let's just remind ourselves really quick how that works. All right, so we'll look at our Stern-Gerlach Z-box one more time. Again, you're going to look at it in the homework, so I'm not going to spend too much time on this. Right. we have two possible basis states, phi plus and phi minus, which we just defined to be 1, 0, and 0, 1. Right? That means that any wave function, which is any arbitrary state of this atom, is equal to some number C plus, phi plus, plus or minus, it doesn't really matter, C minus, phi minus. Okay. And these have some properties. The probability of observing phi plus or phi sub I, whichever one it is, phi sub I is C sub I squared. And the total probability of this case is going to be C plus squared plus C minus squared. And that has to equal 1 because those are the only two options and the total probability has to equal 1. Okay, so we have a constraint for our system. It turns out this is not something we're going to worry about too much in this class, but it is something to think about. The question is what is the step? What kind of numbers are these numbers? And we can see here that they're real numbers, right? Because the square of them has something to do with probability. Probability is a real number, right? It has to be. There's a real probability of observing something. So C sub I squared has to exist between 0 and 1. It can't be any other values. Yeah, give me the answer in just a second.
Okay.
Let me finish my sentence.
Yes.
All right, so C plus or C minus, they have to be squared, absolute value squared has to be between 0 and 1. So what numbers can C plus and C minus be if the absolute magnitude squared is a positive number? That means C can be negative. It can also be complex. So C is a complex number. All right. Right, and a complex number, I mean, is imaginary, right? It's a number, Ci is some Ai plus some number Bi times the imaginary number I. Right, but we're going to assume most of the time that it's typically real, all right? Most of the time in the class, we're going to assume it's real. There's going to be situations where it's useful to talk about the complex version of this. So I just want you to keep it in mind. Typically real. Typically, we choose real numbers. All right, we just set B to be 0. We'll see that there are useful cases when complex numbers are essential. I'll try to explain why. Go ahead.
I was actually a Q answer.
All right, excellent. All right, so again, this is very abstract, but the cool thing is that this, in some sense, gives us everything we need to know about the state of the molecule itself. This is all, when it comes to deflections at the moment, this is all we need to know about, right? This completely defines the results of that silver atom in the deflection experiment, in the z-axis. Remember, we've chosen basis states that are defined based on the z deflection. They don't tell us anything about the x direction. All right, so if we wanted to take this wave function, which is a z wave function, it only talks about the z direction, and we wanted to convert it to something in x, there's a process to do that, but that would require us to develop a new set of basis states that are defined based on the x value deflections. All right, so we would basically convert from one basis set of basis functions into another one that's defined based on the x's. And there's a process of doing that. But in some sense, all we're doing is changing our view from z to x. Right? There's two things that we need to think about in that, just kind of hypothetically. One is that, well, what's that process of going from z to x? What if we have some z result and now we want to go to x? How do we change our wave function to represent that? That's one pathway. And another question you might have is, if I choose some basis, some experiment like the z deflection, are there other experiments that are compatible with this? Remember, we showed that z and x are not compatible measurements. That was one of the first results in this class. But are there other experiments we can do besides X where it doesn't contradict the results of the Z, right? It doesn't lose any Z information, right? So are there other experiments we can do with our Z-defined atoms that continue to be Z-defined? And the answer is yes. In fact, what we're going to see is that when we make a choice, like a Z direction for this deflection basis, this is actually all we need. We can choose to think about the X if we want, but in order to understand, say, the hydrogen atom, where this becomes essential, you don't need to use the X. You make a choice of either Z or X, you don't have to use both of them. You can only need to use one of them. And so it's okay that we lose some information about the X, because what we're going to find is there are other measurements we can do that are compatible with Z that basically allow us to define the atom completely. All right, so we still get a complete picture of the hydrogen atom. There's just some inconsistencies or incompatibilities that we have to make a choice about which ones to choose. Right, so we're going to find out that this doesn't limit us too much, but you can imagine it might be limited, right? Because we could define this basis, and this is the only thing we can know about Z deflecting atoms, is whether they deflect up or deflect down. Can't measure anything else about them. The moment we do, they just disappear. We wouldn't want that. This would be a useless thing, right? It's not a very useful experiment. It only gives us one piece of information. So obviously, we're going to have to start searching for things that we can learn about Z deflecting atoms that gives us more information about that atom. And thankfully, there are plenty of things we can actually define the atom precisely with this representation. But that's a little ways away from that. So now we have this wave function that's length 1. It's a vector. We'll talk about it being a function, I think, Wednesday. We're missing half of our Stern-Gerlach experiment. So let's go back a couple days, couple lectures, and just remind ourselves where we were. I'm going to actually pull up an older lecture than this. And the homework deals with this idea quite a bit. So here's our BZ boxes. So what we've done is we've come up with a description of what the atom state is. So we can have a language to talk about the way the atoms may deflect when entering a splitter. So we kind of, in some sense, know what the silver atom is represented here and then over here. You can kind of get a sense of that, and you're going to explore that in the problem set. Just vectors. But the question is that we have to pass, in some sense, if you think about this as a mathematical operation, we start with a vector. Our silver atom is a vector that's being fed into some BZ box, as we call it. And then out of that box, the deflecting atoms get split, right? You get a plus and a minus. And each of these output streams also have a wave function system. Right, and in the homework, I have you kind of walk through this to figure out what those states are. Right, what vectors represent the silver atom as they go into the box, and what wave functions represent the silver atoms as they exit the box. But now the question is, right, from that perspective of taking a vector, right, we take a vector, and somehow we convert it either into a different vector or a set of vectors. Right, there's some resolution of the vectors going on inside of this box. Something is into the vectors. They may be measured, they may be changed, who knows? And so the question now is how do you represent that operation? Right? How do you, if we have vectors going in and out of boxes, what's the structure of the box from the point of view of that? So that's, now we come to the idea of what's called an operator. An operator is an object that operates, does something to a vector and returns a vector afterwards. Okay, so think of a box, an operator.
A new vector?
What's that?
Returns a new vector?
It may return a new vector, it may return the same one. We'll have to think about that. But the idea is we're going to think about these boxes as effectively functions, little operations that take one vector, an input vector, and spit out another. Okay, so this is what's called an operator. There's other terms for it, but we'll call them operators in this class. And I'll give you some really nice examples of some operators now. All right, so this is what's called postulate 2. Right, and it's the act of measurement. So talking about measurement and manipulation. Through what's called a linear operators. All right, we're going to study operators in this class quite a bit. Okay, and that sounds like a really scary term. What the hell is an operator? You guys have worked with operators in math class before since elementary school. You just never heard them called this way. So let me give you an example of what an operator is. We have to be very specific about what kind of operators we use, but in general, an operator is an object that maps a set of numbers or objects we'll think numbers because we're doing math to themselves. Okay, so the idea is that if you have an operator that feeds in a number, it spits out another number. Have an operator that feeds in a vector, it spits out another vector. If you have an operator that feeds in a human, it spits out another human. All right. So it doesn't change it's not like a function that takes two numbers in. And well, it might do that. Take two numbers in and return another number. It's not going to do that. What it's going to do is it's basically a map of some space of objects back onto itself. So we can think about measurement and manipulation of wave functions. Operators are objects that take wave functions and either return a new wave function or the same one. All right, so here's a great example of an operator that you guys have learned for, let's say roughly 20 years you've known it. Right, define the plus operator such that plus a b is equal to a plus b, which returns a number c, right? Which are numbers, right? So plus 1, 1 is 1 plus 1, which is equal to 2. Okay, so there's a plus operator. So the plus sign is an operator. Minus sign or the time sign is an operator. Okay. And it's not hard to show, but there's two other operations in the real numbers, right? There's division and subtraction. And those are actually just inverses of plus and star. So they're effectively the same thing. So the real numbers have two operators built on them. The real numbers are constructed with two operators. Plus and star, right? Which you know exactly what they do. 1 star 1 gives you 1, 1 star 2 gives you 2, and so on and so forth. And their inverses, which are minus and division. Okay, so it turns out that you can take a whole class on this. This is what's called rings, groups, and fields. Operators impart a structure on a set of objects, and plus and star impart a structure on the real numbers in the sense that you can combine two numbers with one of these operators and get a new one. And there's also a way to go backwards. Okay, so you can think of plus and minus. You have this big box of real numbers. Plus and minus take two of those real numbers and return another one in the box. Okay, so that's an operator. There are other operators. You spend 3 semesters of calculus learning operators. The derivative is an operator. It's a function. It's an operation that takes a function and returns another function. The integral is an operator that takes a function and returns another function. If you integrate over a bound, then it's a function that returns a number. But regardless, These are also operators as well. And we're going to see this in this class. We're going to look at the derivative, taking a derivative of a wave function as an operation on the wave function. Okay, this allows us to have some algebra to our language. We're going to build an algebra out of this that allows us to talk about this idea of operators, allows us to talk about one, what are valid operations? What are valid things you do to a wave function? And two, if we combine operations, we do multiple measurements in a row, which ones are compatible and which ones aren't? It turns out that once we'll go through this math, the idea is that you can, by using this operator idea, you can determine exactly which measurements you can make without them being incompatible. What are compatible measurements? It's going to be how we construct representations of atoms. Is by choosing a set of operators that we are compatible, a set of boxes that don't manipulate or change the state. And once we have that, we can slowly build up more and more information about our atom, and that will give us a complete picture of it. So identifying the operators that are compatible in an experiment, the boxes that are compatible, is just as important as defining the object of the wave function of the atom itself. Okay. So, but again, here's the thing that's odd. Right, these are numbers, right? These are moving numbers to numbers, but for our wave functions are vectors. We have to think about what is the structure of an operator, an operation that takes a vector and returns another vector. So let's go look at vectors really quickly and see what operations vectors have on them. So x2. Vectors have two inbuilt operators. And we're going to see they're not helpful for us. Right, the first one is the plus operator. Right, and that's the idea that you can take two vectors A and B plus C and D. So you got vector 1 and vector 2. And you get a new vector 3, which is just the sum of the components, right? You tip tail, A to C, B plus D. Okay, so that doesn't really, that does help us, right? It takes two, it's an operator that takes two vectors and returns a vector. All right, that's one. The other one is scalar multiplication. Right, and all that is saying is that if you have a vector CA times CB, this is the same as the number C times AB. Okay, right, you can just factor out a scalar. So that's not really, this is a multiplication of a scalar. It says that a scalar times a vector returns a scalar, or a vector. Okay, so that doesn't really help us either, because it doesn't really give us the information we want. We know when we have a box, we're putting a vector in, just one vector in. Right? The SC box, we put in a vector of silver atoms, and out comes two streams of that silver atoms. So there's only one wave function going there. It's just the vector, the system of silver atoms wave function. So whatever operation the box is doing, the only input it has is the vector of the state vector of the input atom. There's no scalar multiplication, and there's no addition because we're not combining vectors. So there has to be some other property, some other operator, some other operation that maps vectors to themselves that isn't just plus and star of scalar. Now, and this is a idea that I'm about to introduce to you that you don't really learn in math class. You learn it in a class called linear algebra, and that's just for historical reasons. When quantum mechanics, one of the reasons why it was so hard to develop quantum mechanics is because the physicists that developed it had to learn linear algebra. They hadn't learned linear algebra yet. Linear algebra in the 1900s, the idea of vectors and eigenvalues and eigenvectors, all these things that we've talked about, we haven't mentioned all yet. But as we'll see, these concepts that we see in this class about vectors, these things have been around for a long time, mathematically. Linear algebra has been around since the 1700s, but no one applied it to anything until quantum mechanics. And that was actually a big change. Quantum mechanics introduced linear algebra, and general relativity, Einstein's relativity, introduced this concept of differential geometry, the idea of surfaces and manifolds, differential spaces of multiple dimensions. New types of math had to come into physical science that physical scientists had never studied before. So it's kind of a weird concept how we impart this structure that we're going to see with vectors and stuff onto the real world, because we don't really learn about the real world from this perspective. It's a new perspective on how things work. And they had to learn it as well. So the question that people had then, and this is what a very famous physical scientist named Werner Heisenberg, the namesake of Walter White on Walter White's drug pen name for Breaking Bad, Heisenberg. Heisenberg came up with this idea. He said, we're going to have our atoms represented by vectors. What kind of structure is imparted on the boxes themselves that do measure manipulation? And Heisenberg had a really brilliant idea. None of this is obvious. There's not really an obvious way for me to convince you that this is true, other than showing you that it works. But Heisenberg's insight is this. If a wave function is a vector, then a measurement is a linear operator, is an operator with the structure of a matrix. What the hell is a matrix? You guys might remember from Algebra 2, we learned a little bit about matrices. What's a matrix? Well, it's just a square or a rectangular object that contains numbers at rows and columns. So let's say, for instance, you have, right? So a matrix is like a two-dimensional vector, not in components. Not in number of components, but dimensions of components. So you can think of a vector as a list of numbers, right? So a vector is a 1D line of components, right? It's A, B, C, right? So on and so forth, right? So you can just list them in a line, a column effectively. A matrix is a 2D box of components. Right? It looks something like this instead. A, B, C, D. So let's see how that works. So my claim is that if we treat our boxes as operators, which are matrices, then when we operate on a vector, a wave function, we get a new vector out, which is the output of that box. So let me show you a good example of this. You're going to do a ton of this on the homework. But let's just look at an example. Right? Let me prove to you that multiplying, basically operating on a vector with a matrix gives you another vector back. All right, so let's just do an example. Right? All right, so let's just say, for instance, that our wave function is 1, 1 times 1 over the square root of 2 to make it length 1. Okay, this is a 50-50 mixture. of plus and minus. Okay, and let's let our matrix of our box, whatever we're feeding our vector into, to be 1, let's just try something. 1, 0, 0, minus 1. Okay. Imagine, you might wonder, well, where the hell did I get to the 1, 0, 0, minus 1? I'm just making it up for now. Okay. Because actually, this matrix does have some interesting properties and the problems that talks about it, but just bear with me. So how do we do this operation? The idea is that this matrix is going to be applied like a function. Think of it as like f of x, where x is a vector. The vector is going to be applied to the matrix, and the matrix is going to do something to it to spit another vector out. Okay, so what I should expect is that if I take my matrix and apply it to my wave function, I should get some new wave function out. Okay, so let's see how that math works. Oh, I forgot. There's one more operator for a vector. We should use this one. I'm sorry. So let's figure this. Let's go back again to just vectors. The things that are imparted on a vector. There's plus and there's star. There's one more. Does anyone remember what the other operation that vectors have? What happens? What do we call it when we take two vectors?
Product?
Well, there's the cross product, but that only works in certain scenarios. What's the more general version of that? Dot product. What's a dot product? That's what you take two vectors and you get a number out. Remember, the dot product tells you kind of the angle between the two vectors. So I forgot about the dot product. The cross product is a, I don't know how to explain it. It's a expansion. It's a consequence of the dot products. It's an application of it. Yeah. So there's also the dot product, which says that if you have vectors v1, a, b, a and b, and v2 is c and d, then v1 dot v2, remember, is the
Oh, it's AC plus BD.
exactly. So it's the sum of the products of the components. So you take the first two components and multiply them together. So that would be a times c. Sorry, I got a little messy here. And then you add the second set of components, which would be b times d. Okay, which is a number. Okay, so this takes two vectors and maps it to a number. Okay, there is the cross product, but the cross product doesn't work for everything. The real version of cross product is called a wedge product. The general cross product works in any dimensions. Cross product only works in 3 dimensions. There's not really a 2-dimensional cross product. It's called a wedge product. We're going to talk about wedge products. It's way beyond our understanding. So we're just going to assume these 3. These are the 3 that matter. Okay, so now that we have our structure, right? We know vectors can be added together. They can be multiplied by a scalar, and they can be dotted together. So the only thing a vector can do is to something is one of these 3 options. Okay, and so the trick is that actually what happens is we know that in the end, we have an operation that looks like this, and we know we're going to get another vector out with 2 components at the end. Okay, that's my claim. It's that a matrix operating on a vector gives you another vector, right? It's a mapping to itself, to the space of all vectors. So the way this is going to happen is we have to take dot products of things in the matrix with the vector. The way to think about a matrix like this is that it's actually a vector of vectors. Let me show you what I mean by that. Imagine if I instead wrote this generic vector as this generic matrix as a vector where each component of the vector is a vector. You can also write this equivalently as a horizontal vector, another just a 90-degree rotated one where the columns are vectors. Okay, so you can often think of a matrix as a collection of vectors. And as you start to explore this a little more, you'll realize that in some sense it tells you how when you add one vector to this box, how it connects that vector to other vectors in the space. It tells you in some sense how it moves. And we'll see that very clearly. So since we can think of a matrix as a vector of vectors, then the idea is that we're going to take a dot product of our vector with each of those little vector components of the matrix. So let's look at that. So we've got little vectors right here, little row vectors, right? And the first component of the output vector is going to be the dot product of the input vector times the first row, dotted with the first row. So let me color these like this, right? And then highlight where these are going to end up. Right, we're going to dot 1, 1 with 1, 0 to get the first component, and dot 1, 1 with 0 minus 1 to get the second component. The idea is kind of like I take that 1, 1, I rotate it 90 degrees, and I dot it, moving it down vertically through the matrix. Like I feed it row by row. I dot here, and then put the result over there. Dot to the next row, put the result over there, and so on and so forth. So the result of this would be therefore, for the first component, the dot product of 1, 0 of 1, 1, which is 1 times 1 plus 0 times 1, which is 1. And the second component is going to be 1, 1 dotted with 0 minus 1. The 0 cancels out the first one, and we add minus 1 times 1. Okay, so what does this matrix do to our vector? Well, it took a vector 1, 1 and converted it to 1 minus 1. So let's look on a coordinate system what this looks like. So the vector in this direction is 1, 0. Direction in this vector is 0, 1. This is minus 1, 0. And this is 0 minus 1. We can, that's our parameter space. I'm not using pluses and minuses here, just numbers. These are our two base states. And so our initial state, which I'll draw in blue, is 1, 1. So it's pointing in this direction. So there's our initial state. It has component, right? It has component 1, 1. Right? And we apply this matrix to it, right? Which takes this vector and converts it to 1 minus 1. So let's draw the final vector. And that's pointing in the bottom left like this. Right? So this is psi out. And this is psi in. Right? And so what does the matrix do? The matrix takes that vector and rotates it pi radians, 180 degrees. Right? It's a 180-degree rotation of the state. Now, do we see anything different in our measurement when we split the atoms in plus and minus? No. Because remember, the probability of observing a result is the square of the component of the vector. So in the initial state, 1, 1, we have to normalize it to 1 over the square root of 2. I forgot to do that. Get probabilities, right?
You can do that after.
Yes, of course. Yes, you can always. In fact, when we do functions and we do wave functions and functions, we'll always normalize afterwards. Yeah, you basically create, it's easy to just create the vector and then divide it by a number so that it's length 1. That's the easiest way to do it. So let's look at the results of our initial vector. Our initial vector is 1, 1 over the square root of 2. All right, so that means that the probability of observing one of the results is the square of those components. So the probability of observing it psi up is 1 over the square root of 2 squared. That's 1/2, 50%. And the same for the bottom, right? Same for down, 50%. So this is a 50-50 mixture of up and down, superposition of both. And then we rotate it 180 degrees And the result of our deflection experiment is exactly the same. Still 50-50. Yeah, go ahead.
So when we're doing the multiplication of the matrix and the vector.
Yeah.
So you said that the matrix is like a component of the
It's a
two
vector of
rows,
vectors.
or it could be the two columns.
Right. So
We
this
don't
is a
multiply
great
columns, though?
great question. So the question is so what Angie's asking is, why did I choose it to be rows instead of columns?
Yeah.
That has to do with the some rules in algebra. Can we answer that question after I finish this?
Yeah.
That's a good question, and I think it's a good algebraic point. When do I choose which one to use? That's actually a good question. Let's go back to the result really quickly. So if you look at the deflection detector, nothing's changed, still 50-50. But remember last class, we said that there's now this -1 sign in the wave function that you can't factor out, right? Because if you factor out a -1 here, you get -1, 1. That puts you up here. Okay, so you don't end up even factoring out any numbers. You don't go back to the original state. Okay, so there's a phase difference of pi between the two, a phase difference. Remember, we think about these, if you think about these in time, you imagine that these wave functions are in time. You add time to that, and they're just oscillating around the circle like this. Okay, imagine they were both moving around the circle at the same velocity, psi out and psi in. No matter what you do, they're always pointing in opposite points, which means that they're out of phase in the cycle. One is, in some sense, halfway through the cycle faster than the other one. When one completes the cycle, the other one is halfway through it. Right? We'll see that when you do things in time, do spectroscopy, for instance, or computing with those numbers, that becomes important when you add time to this. But for us, it doesn't matter so much. The important thing is if it changes the state. Right, we go from one state, one representation of our system to another. It doesn't change the measurement results, but it does change the phase structure. And we're going to see that that can be important. I think I described to you guys last time that if you take, right, if I took this silver atom and combined it with this silver atom and created a set of a product state of the two, I added them together and combined them together in a new box. I'm adding 1, 1 to a vector 1 minus 1, and the components add. The resultant vector would be 1 plus 1, 2, that normalizes to 1 in the first component, and then you have 1 minus 1 in the second component, that's 0. So when I add a 1, 1 and a 1 minus 1 in a combiner together, I get 1, 0 out. If I add a 1, 1 to a 1, 1, I get a 1, 1 out. Okay, so the behavior of these two atoms are different in the next box. They are different states, but they have the same measurement results. But when you combine them with other silver atoms of different states that have the same measurement results, like I do here, you get different outputs in that combiner. It's very interesting. I want you to hold on to that idea of phase. It's going to come back and I want to say bite us in the ass, but it becomes extremely important when we start talking about wave problems. What we're going to do is we're going to realize that the reason why things have phases, things move around on a circle like this, is because they're like waves, and that's what waves do. They move sines and cosines. So remember, sine and cosine is just the position on a circle as you move around a circle. And we're going to see that the functional forms of these things are sines and cosines. They're waves that move around in an oscillatory fashion. And so it's not surprising that we see something that looks kind of like a phase here, where two things are at some point pointing at different points of the circle and moving it around the circle in a different way. Okay, so that's interesting. That doesn't really change our measurement, but it does change the state of the atom. Are there other types of boxes that we can put in that don't do anything? Let's look at something else.
Oh, wait, were we going to talk about the...
Oh, yeah. So the side point. Yeah, thank you. This is a good algebraic point. I want to call it by operator algebra.
Wait, is it based off of which way the vector is?
Yes.
Okay.
Yes, absolutely. Okay, so let's say, for instance, you have A, B, C, D. You have a matrix A, B, C, D. right? And your wave function, we haven't derived this yet, all right, but we will. We're going to show eventually. I've already given you a sense that the numbers and wave functions may be complex. One of the properties about complex numbers, just like our wave vectors here, is that you can switch the sign of the imaginary component and still get the same vector, the real component of the vector. Let me show you that in a second. Actually, let's talk about that right now. This is a really interesting point, and I don't want to get too deep into it, but I think it's important. But remember, if you remember something about complex numbers, right? We should talk about it now. A complex number C is a real number A plus a real number B times the imaginary number I. Right? What is I again? Does anyone remember?
The square root of -1.
Yeah, square root of -1. We're never going to, I mean, there's sometimes where that's useful for algebra, but just think of it as a special thing. And the best way to think about a complex number is that it's also a vector. We can call it a vector AB. Right? And the coordinates of this vector are the real part of C and the imaginary part of C. And so that vector is pointing at some point A, comma B. Right? So there's our little complex number AB. And this is the real part, which is A, and the imaginary part of the complex number, which is B. All right, so think about them as vectors. So what's the length of that vector? So the length of C is A squared plus B squared, absolute value. Sorry, C squared is equal to A squared plus B squared. Right? So the length of C is equal to the square root of absolute value of A squared plus the absolute value of B squared. Right? This should look a lot like our normalization of vectors, except these could be any length. So what can A and B be where you get the same C no matter what? Well, it doesn't matter which direction A and B are, right? A and B can be positive or negative, and you get the same length. All right, so same length right? So you have there are 4 vectors that have the same length. There's this one, that one, in the same direction, and this one, right? There's 4 of them, just like we saw before. Okay, and there's a special vector, but we don't consider all 4 of these. There's one in particular we care about. It's what's called the complex conjugate. It's the one where the B switches signs. So there's a special number which we call the complex conjugate. C star. We write either C star. Sometimes I'll write it as C with a little dagger on top of it. Right? And C star is just A minus BI. All right, so we take the I and we flip it negative. That's all that we do. Okay.
So now it's the negative square root of -1.
Yeah, and so now what happens if I take C times C star, if I take a dot product of these 2 vectors, this ends up being A squared plus B squared. Right, that kind of looks like C squared is equal to A squared plus B squared, looks like I expect. Right, because it's A minus BI plus times A plus BI, and you FOIL that out, and you get A squared plus B squared. Okay, so when we take a complex number and multiply it by its complex conjugate, we get the length of it back. So the square, I'll write that here, the square of a complex number is its length or its magnitude. Now, why is that relevant here? Why do I even bring that up? Well, it turns out that Angie's question actually is directly related to this concept. So let's imagine I have a two-dimensional vector or two-dimensional wave function, but remember that the components may be complex. They may be complex numbers. So we could write these instead as a plus b plus I. That's the component on the first one. And a minus plus b minus I. Okay. That's our vector that has complex numbers. There is also a complex conjugate of the wave function, which is a plus minus b plus I. And a minus b minus I, right? We just switched the signs, right? So if this is psi here on this picture over here, then the complex conjugate is just the one on the opposite side of the y-axis, 90 degrees. Why is that relevant? Well, it turns out that we're going to see that when you take a complex, we're not going to see this in this class, actually, maybe not. But we'll see something similar to it. When you take when you have a wave function that's a complex vector, that's a column, and you take the complex conjugate of it, which means it's the negative complex version of it, then that's equivalent to taking a column vector and making it a row vector. Let me show you what that means. So we have m times psi, which is a, b, c, d, a plus b plus I. I'm not going to do the math of this, but I'm just going to set it up for you. And a minus plus b minus I. Okay. This is equal to, and remember what we do here. We take this vector that I circle here. We get this, and we get two entries, one here that's red and one that's purple. And those are constructed by taking the yellow and dotting it with this vector and this vector from the right. All right, the important thing is from the right. We dot right from the right. This is the same thing. If I write the vector, the matrix on the right, and then I write the vector as a row vector instead of a column vector. So it would be a plus b I and a plus plus a minus plus minus I, like that. So I have them rotated 50 degrees. So this is a column, and then this is a row. Oh, and I forgot sorry, they need to be the complex conjugates. I apologize. So this is a plus minus b plus I and a plus minus b minus I. And so I can draw this as a row vector, and we're going to dot it with the column vectors instead on the right. And when you do this math, what you find is you get the same answer. Okay, so that's why we look at both of them. If our function is complex, if we have a complex function, we may have to use this secondary math, not in this class. I don't think we'll ever be in a situation where this is necessary, but this is why there are rows and there's columns, and why we can represent the matrix as a column vector of vectors or a row vector of vectors. Right? It just depends on how we do the math. The important thing is that operator algebra, unlike math, unlike regular algebra, operates right to left. right? So the idea is that, well, anyway, the idea is that you evaluate the most right thing and then work your way out. Okay, instead of N word like we would. Right, we'll see that as we go. Right, that's kind of an excessive point. But that's why we use, this is the structure that comes from the fact that we use complex numbers. You have to deal with these.
So this class will always be using the.
We're always real numbers. There will be a couple they're always real numbers. There's a couple places where we might need to use complex numbers to describe a certain property. Because there are properties in the world that are complex. I mean, there's no other way to describe them. But we're never going to really talk about complex wave functions because it's just confusing and it doesn't really help us. Right, but I want you guys to have at least a picture of the complexities and kind of the structure that's underlying everything, and just understand that we can make choices in quantum mechanics to simplify things and to do things in real values. We lose some information as it turns out by choosing purely real numbers and not using complex. There are places where we absolutely need complex numbers, but there are in most places in chemistry. Remember, in chemistry, we're dealing with real objects, so it's generally okay to use real numbers. There's some other tricks that we'll find that even if they're things that are complex, we're guaranteed to get real measurements out of them. Okay, that was a big aside. I apologize, but it was a good one. So let me go back to this matrix again. Again, the idea is that the matrix takes this vector and changes it and moves it in space to points to another state. Okay, that state has the same output, still 50-50. But in some sense, it's pointing in a different direction. It's going to have different physics. And if you combine these two, they're going to interfere with each other like two waves. Let's look at another example, a really simple example. And in fact, this is something you do on the homework. Right, what we're going to define a matrix 1, 0, 0, -1, right, with basis phi plus 1, 0, phi minus 0, 1. You're going to play around with this matrix a little bit on the homework. Well, let's look at the same operation again. All right, let's apply this matrix to a bunch of different random states that our silver atom could be in and see what the result is. Right, I think it's first relevant to think about what happens when we feed just an up deflecting or a down deflecting atom into this box. All right, not a mixed state, just a pure, boring old phi plus or phi minus. You're going to do this work. You're going to repeat this on the homework, so it's a nice practice. Zero. Okay, remember that we take our input vector, psi, and we dot it with the first row, and then dot it with the second row to get the first and second components. So the first dot is going to be 1 times 1 plus 0 times 0. And the second one is 1 times 0 plus 0 times -1. Well, that's really easy, right? It's about the easiest math you'll ever do. And of course, this gives me 1, 0. So this is interesting, right? So when I feed a plus electron into it, it returns a plus electron. Right? It doesn't change the state at all. It just goes out unimpeded. All right? Nothing has happened to it. Let's look at the next one. Phi minus. Same idea. But now instead we have a 0, 1 instead. And it's probably not too hard to see that we're going to get a 0 in the first component. And we're going to get a -1 in the second component. All right. Well, that may look like a different state to you, right? It's moved. Let's see. It's moved from this way to this way. It's pointing down in that axis system. But remember, one of the operations that we can do with vectors, we can factor out a scalar. And there's a really easy scalar we can factor out, which is -1. So really what we can do is write this as our original vector times -1. And consequently, we can do a very trivial thing and say that this is 1 times the original vector. Right. So now we have a new structure on the outside. We have, now what's happening is that it's not rotating the state, but it's returning a scalar. It's in some sense, it's stretching or changing the length of the vector, but it isn't changing the direction. Right? The first one does nothing. It returns the same vector, but the second one multiplies it by -1, right? Which means it changes both of the, right? It changes the whole thing by -1. Not just one of the components, but everything by -1. Right, and let's finally look at times a combination vector. Right, the 50-50 vector. Which time do I got left? Good. 1, 1. And what we can see is we get a 1 over the square root of 2. And we get 1 minus 1. All right. So this is just a pi rotation. Right? It's just like we saw before. Right? It's exactly the same result that we had previous, which is I took the original mixed state and rotated it by 80 degrees, or 180 degrees. All right, but here's the interesting thing, right? So that's different, right? That's a new state, right? We can agree that there's no way to factor out a scalar here to get the original state because one of the numbers is multiplied by number -1. So if you factor out a -1, the other one's going to be -1. So there's no way to factor out a scalar to get from here to here. At least as far as we can tell. Okay, so in some sense, the behavior of M acting on the base states is different than the linear combination. Right? And so now we have, in some sense, 2 different outcomes to our operation. One is that it can change the direction by 180 degrees, or it doesn't change the direction at all when you feed in the basis states into it. And this is actually the definition of a basis state. So what we have now is we've identified 2 vectors that when measured by the matrix M are left unchanged. They're left unchanged. And then there's another vector we put in that does change. So there are vectors that for a matrix that are left unchanged and variant, that are stay the same on the output as the input. They may be multiplied by a scalar, but they're the same direction. And then there's a set of vectors whose direction changes. Right? Well, I want to characterize these 2. Right? And in particular, I want to focus on the 2 that don't change. These are very important. It's the first time we've seen this. Every other operation we've done in examples has changed the direction. But now I've identified for this matrix 2 inputs that give you the same output. And in fact, this is the definition of a basis state. So a basis state for a measurement corresponding to an operator, right, which we'll call phi I, satisfies, right, let's call that operator O hat, satisfies that O hat applied to phi I. Right, so when we measure phi I with O, our little vector or matrix, we get some number back. We'll call it A times phi I, where A is a real number. And it turns out, as we'll see later on, it has to be a real number. Right, this is interesting because this actually turns out to have a really strict thing. What I just stated to you about 10 minutes ago was that the wave functions may be complex. They may be complex. They may have complex numbers. They may be really confusing. But one thing that we're going to see is that if you can determine which these states, these basis states for a given matrix, a given operation of measurement, that are unchanged, right, that don't change, then you're guaranteed that the number that they return, this eigenvalue, is always real. Even if they're complex, even if everything is complex, the operator and the wave functions are complex, they have to satisfy the property that if the wave function is unchanged by the operator, meaning you just measure the state. That the thing that it returns, that scalar, is a real number. It has to be a real number. It can't be complex. If it's complex, it's not a real measurement. All right, it's guaranteed that this number that's returned, the scalar, is real. Has to be required. We're going to see where this fails later on. Okay.
It has to be, except it will fail.
Well, it will fail, and then we'll realize that that means that it's not a real measurement.
Oh, okay.
It's a hard bound. It's like a hard restriction.
And the failure tells you.
Yes,
that
it's no good. Exactly. And so if we define a matrix and we find that there's a set of states that do this, that when you put them through the matrix, they come out the same times a number. These are called basis states, and we call them specifically, what we say is that phi I, there's a term for it we use in German called an eigenvector or eigenstate. Do you know what eigen means? Anyone know what eigen means in German?
It's like single.
Yeah, it means unchanging. It's the same. And AI, or A, we'll call it A sub I, just though there might be different values depending on the phi, is called the eigenvalue. And the most important thing about the eigenvalue is it's the output of your measurement. It's the value of the measured property. What does that mean? Well, let's go back up to our newly identified eigenstates of this matrix M, right? 1, 0, and 0, 1. When you apply M to them, you get 1, 0, and 0, 1 back, right? And they're multiplied by +1 and -1. All right, what the hell does that mean? Well, these +1 and these -1s, these are the eigenvalues of this operation to the eigenvectors, and they correspond to the readout that the splitter box gives you. -1, this tells the computer or the deflector, right? It's the response of deflect downwards. Right? You go minus, and this is deflect upwards. You go upwards. Okay, so what are the construction? How can I say this? What are the components of our experiment? Well, we have an input state, some phi. We have a measurement or an operation, which is a matrix. And we apply that operation to our input. And if it's a valid state of that input, we get back. So an eigenstate of the input, we get back the original state times an eigenvalue, which is the readout on the screen for the result. So the eigenvalue tells you the answer for the experiment. And the wave function is just the output electron. It's what comes out. So when we have a deflector box and we run in a stream of electron or argon or silver atoms that are either plus or minus, one's going to go through 50% chance it's plus. So 50% time I'm going to get a +1 out. It's going to go ping. And then 50% time it's going to deflect down, or it's going to return a -1. It's going to and I'm going to hear boop, boop, boop. I'm going to it's going to go back and forth forever, 50-50. On average, I'm going to see 50 of each of them. Right? So the eigenvalue is the measurement, it's the property. It's the quantity that we are measuring in our experiments. And the eigenvector is the object itself that is, when being measured, returns unchanged and returns the value of the measure, the eigenvalue. So here's the trick. Right? This is in some sense the trajectory that we need to take. We have some new system that we want to study. One of our targets in this class is going to be the hydrogen atom. What is the hydrogen atom? It's a proton with an electron at some distance in an environment where they're attracted to each other, and that attraction depends only on their distance and not the direction. The electrostatic attraction between a plus and a negative charge follows the same physics as gravity. So it only is a function of the distance. The potential is 1 over r, so it's a function of the distance, and not the angle. So you can kind of think as the proton is this thing that attracts this electron in a spherical way, and the electron is sitting somewhere in a sphere orbiting this proton. Right? So we have to come up with a wave function for that, right? How do we do that? Well, the way we do that is we create a box that measures the property that we want of the hydrogen atom. Maybe we want to measure the average distance between the proton and the electron. So how would we do that? Well, we would set up a camera that took a hydrogen atom, and every once in a while, every 10 million times a second, we'd take a snapshot and record at what distance that electron is from the proton. There's some random distribution. Sometimes it's real close, sometimes it's real far, sometimes it's kind of in the middle. Right? It's going to be random, and we can mark where those are. All right, and we'll get some average value. Right? We'll get an average value for the average distance between the electron and the proton. And that average distance corresponds or is related to this eigenvalue that comes out of the box that we construct to make this measurement. So we've got a box that it can be represented as a vector, or sorry, as a matrix. This photograph box acts as a matrix. We feed in our electrons, our hydrogen atoms, take pictures of them, and we take pictures, and every time the hydrogen atom comes in and comes out the same way, we take a picture and we save it. And the average of those pictures, the average of those distances, is the average of the eigenvalues of the electrons or of the hydrogen atoms that are passed through there, and what is returned by the instrument. Okay, so by measuring averages of properties or calculating eigenvalues, we can calculate experimental averages because it tells us the output of our result. Right? We put an electron in, silver atom in, it bounces up, we get a +1. One goes down, we get a -1. And we can keep tallies. Same idea of hydrogen. We can measure the distance between the hydrogen, the electron, and the proton, get an average, and that average corresponds to the average of the eigenvalues for that system. So the goal is to build a box that does the measurement we want, then come up with a construction for how we represent the hydrogen atom from the context of that box, and then start measuring what are the possible configurations of the hydrogen atom that when we put them through the box, we get the same thing out. Right? The box does not leave the hydrogen atom changed. It leaves it unchanged. And what's going to happen every time that does is that every time that passes through, the electron, the photography system is going to spit out a picture of where that electron is. And by taking averages of those pictures, we come up with statistics about the average position of the electron, which is calculable exactly from the values of the eigenvalues. Right? So eigenvalues have something to do with measurement results. Eigenvectors have something to do with the state of the thing you're measuring. And operators are the objects you're doing the measurement with. Okay? So what we're going to do is we're going to put these all together next time, and we're going to ask that question again. How do we take this idea of vectors and convert it into space? How do we start thinking things about X and Y? When we think about the position of the electron and the hydrogen, it's going to be really important for us. So we'll start to think about how we can take these vectors and move into something that looks like a function of position. All right, that'll be our next step, guys. This is all you need for the homework. The rest of it will be for homework 2. Have a good one, guys.
Thank you.